think I need to. Okay, so let's have a look at the infinite Erdos-Szekeres theorem, which essentially states that in a totally ordered set, if you have any infinite sequence, it will have a monotone subsequence, either increasing or decreasing. Okay, it will have a monotone subsequence, either monotonically increasing subsequence or a monotonically decreasing subsequence. Okay, there's a very interesting idea to this. Okay, let's try to picture the idea first. Okay, by putting some kind of tags on it. But so let's say, suppose we have something like this. Let us write a few numbers so that there is a little picture of what is happening. Okay, so this is the sequence. See, there is this, definitely we know that if you look at any term of the sequence, either there will be infinitely many points after it which are greater than or equal to it, or there will be infinitely many terms after it which are less than or equal to it, right? So suppose, so you start with A1, okay, if there are infinitely many points after A1 which are greater than or equal to it, okay, let's put a box on those. Okay, if there are infinitely many points after A1 which are greater than or less than or equal to it, in either case, but both might not necessarily take place, right? In particular, you can have all after it being greater than or equal to. So let's say, suppose these are the ones either all greater than or equal to or less than or equal to. For that particular subsequence, you're going to put a green box. Okay, so A1, I'm going to put a box for A3. Say, suppose these are the ones which are all either greater than or equal to or less than. Okay, so you're going to have these infinitely many green boxes. Okay, now look at the second green box. Okay, to this point. So now you're going to have infinitely many after it which are greater than or equal to it among the green boxes. Okay, among the green boxes you're going to have infinitely many which are greater than or equal to it or infinitely many which are less than or equal to it. Okay, so whatever the case, put green boxes for those also outside it. Okay, so we'll have here A3 has 2 green boxes, possibly A6 would have 2 green boxes, this maybe has 2 green boxes. Okay, look at the next one with 2 boxes. Okay, this again among the ones which have 2 boxes, only among the ones which have 2 boxes, infinitely many will either be bigger than it or less than it. Okay, for those you put 3 boxes. Okay, and we can keep doing this. Okay, for these let's put, so I have gone to the second one and I am going ahead. Okay, so something like this. Of course, you know I can't, this one does not have, let's put for this one at least. And this, you can continue this process, okay, of putting these infinitely, of putting these kind of boxes. Okay, you take this set, you take the sequence of, first you take the first one with 1 box, okay, take the first one with 1 box. So let me just take, in this case let's look at it, we'll have first one with 1 box, that's A1. Then you take the first one with 2 boxes, A3, right? Tell me. How the boxes are put? Okay, so let's start again. So this is a sequence, you start with A1, okay? Either there are going to be infinitely many after A1 which are greater than or equal to it or less than or equal to it. Okay, suppose greater than or equal to it, you put, for everything that is greater than or equal to A1, you put boxes. If less than or equal to it, you're going to put for all of them the same, either all less than or all greater than. So basically the ones which have 1 box will either be all greater than or equal to A1 or all, so you're going to have infinitely many of those. Okay, go to the next one with 1 box, that is now in this case A3. among the 1 boxes, okay, we have already put 2 boxes here, but among the ones with 1 boxes, either infinitely many will be greater than or equal to A3 or less than or equal to A3. Same method, but for those 1 boxes, you're going to now put 2 boxes. Okay, again, infinitely many 2 boxes will come in. Go to the next one with 2 boxes. Okay, this one has 2 boxes, but the one after that is this, which had 2 boxes. And you follow the same process, you're going to put 3 boxes across it. Now, I'm going to pick the points which have the first 1 box, okay, that is A1. Okay, then I'm going to pick the next one which has the first 2 boxes, in this case A3. Okay, then I'm going to pick the one with first 3 box, that is A6, and I would have to carry this on. Okay, this would be the process. Okay, now let's see what are the observations that we can make. Firstly, if I look ahead of any of these numbers, okay, like example, if I look at A1, either A3, A6 and whatever so on will be all greater than A1 or all less than A1. Okay, either all of the ones beyond it will be greater than it or everything will be less than it. Why? Because they are all in the A1, they all have 1 box to them. Right? Everything that comes here will have 1 box for it. So they will either all be greater than or equal to A1 or less than or equal to A1. Okay. Similarly with A3, if you look ahead of A3, right? If you look ahead of A3, they will all have at least 2 boxes. So either all of them are going to be greater than or equal to A3 or less than or equal to A3. Okay, so that makes sense. So if a term has all greater than or equal to it, we can put a up arrow here. Okay, if it has less than or equal to it, everything after it is less than or equal to it, we can put a down arrow to it. Okay, now what does the infinite pigeonhole principle tell us? That you will have infinitely many terms. Either you will have infinitely many terms with up arrows to them, or you will have infinitely many terms of this with down arrows. What will happen if infinitely many have up arrows to it? You pick all the ones with up arrows. Okay, you pick all the ones with up arrows. What happens? Take A1, everything after it is greater than it. Take A6, everything after it is greater than it. Take the next up arrow, everything after it is greater than it. So you got a increasing sequence. While if there are infinitely many with down arrows, then pick the ones with the down arrows, that's going to give you a decreasing sequence. Right? Because everything after it is going to be less than it. Pick the next one with the down arrow, everything after it is going to be less than it. Everything after that is going to be that gives you your proof. Now you have to put it in some kind of notation. So this is what the basic idea is. Let's try to write out the proof. So where have we used the pigeonhole principle? Where have we used the pigeonhole principle? First, to say that there will either be infinitely many after A1, right, with which are greater than it, or infinitely many less than it. That's one place we have used the pigeon. Second one, we have used the pigeonhole principle here to say that there are either infinitely many up arrows or infinitely many down arrows. That's where we have used the pigeonhole principle. Okay, so let's try to write it out. So, so we need to define this sequences, in fact, recursively. Okay, these let me call them as K-box sequences, right? That's what we can think of them as. Okay, so so by the infinite pigeonhole principle, okay, there exists a subsequence. I'm going to call it as A1 comma n. Okay, A1 comma n, n going from 1 to infinity, of an, okay, this is a subsequence of an such that this a11 is basically a1, okay, and either all terms after this are greater than or equal to a1, or all terms after it are less than or equal to a1. These are your one box sequences. These are actually your one box sequences. That's what I'm doing. Okay, the one box sequences. Either a1, if you understand that, you can transfer it into this quite easily. Either this is greater than or equal to a1 for all n, or a1n is less than or equal to a1 for all n. Okay, now among this, do the same thing. The only thing is, with the starting one you take a1, but beyond that you are always going for the next one. You see, we need to go with the next. Here we don't start with all greater than or equal to a3, we would remain on the same sequence. We had to go one forward. Okay, so that's the only difference. But so again, by the pigeonhole principle, you can find a subsequence of a1, a subsequence, let us call it as a2n, n equals 1 to infinity, of a1n, n equals 1 to infinity, such that, see, if this is a subsequence of this, it will also be a subsequence of that, right? Such that a2n, so the first term of this is what? What will the first term of this be? It will be the, see, what is the first term of the 2 box? It is the second term of the first box, right? That's what we have taken. So the first term of the 2 box is the 2 box sequence, right? This is the second term of the first box sequence. Yeah, a12, correct? That's what it is. So this is this, and of course either we have all terms after this greater than a12, either a1n, a2n is greater than or equal to a12 for every n, or a2n is less than or equal to, okay, let's leave this up for some time. Okay, again we can do the same process on this. Okay, so now we could define this recursively. In fact, we are defining these sequences recursively. Given this, I can define this. Given this, I am defining the next one. So I am defining it recursively. So recursively, we can define for t in n, we can define a t comma n, or let's go with t plus 1, t plus 1 comma n. Okay, 2 is actually already defined, no matter. Okay, I think we'll keep t greater than 2, t greater than 1. Okay, we can define, or we can find, okay, in the same way, subsequence a t plus 1 comma n, such that subsequence of, so this, the t plus 1 box sequence is going to be a subsequence of the t box sequences, right? Of the t box sequences, n equals 1 to infinity, such that, what is the first term of this? T plus 1 comma 1 would be the second term of this sequence, right? That is a t comma 2 and everything, what is the first term of the 2 box sequences? It's the second term of the 1 box sequence. What is the first term of the 3 box sequence? The second term of the 2 box sequences, and so on. So this would be this, and either a t plus 1 comma n is greater than or equal to a t comma 1 for every I think a t comma 2, right? A t comma 2 for every n, or a t plus 1 comma n is less than or equal to a t comma 2 for all n. I hope that's okay. Okay, ahead of it, that's the way we go. This is basically the first term anyway. Okay, this is the same as a t plus 1 comma 1, the first term. Is that okay? Okay. Now, what are we picking here? So we've got these sequences. One is we're starting with a1 comma n, a2 comma n, a3 comma n. What are we picking here? First element of 1 box, first element of the 2 box, first element of the 3 box, right? So we let Bn such that we are going to take Bn to be, what is it? First term of the T box sequence. What is that? A T box sequence. First term of the T box sequence is a t comma 1, right? So we are going to take Bn to be a t comma 1. Okay, and since the next term is always in the subsequence of the previous terms of the previous sequence, okay, what we will have is, therefore, either, no, so for every n in n, either what happens is, either all terms after Bn, either Bn is greater than or equal to, or let me say every term after it is, for all t greater than or equal to n, right? Either every term after it is greater than it, or every term after it is less than it. So, or Bn is greater than or equal to Bt for all t greater than or equal to n. Either every term after it, these are the terms after it, right, and equal to it, that's fine. So this is what we have. Now, since there are only 2 conditions, this is your up arrows and your down arrows, right? On n, on Bn I will put an up arrow if every term after it is greater than it, right? And I put a down arrow if this happens. So again, by the pigeonhole principle, so by the pigeonhole principle, either there are, by the infinite, okay, infinite pigeonhole principle, either there are infinitely many n in n such that for every t greater than or equal to n, Bn is less than or equal to Bt, or this will correspond to the up arrows, okay, infinitely many up arrows, or for every t greater than or equal to n, or there will be infinitely many, or there are infinitely many n in n such that for every t greater than or equal to n, Bn is greater than or equal to Bt. Okay, so let's take both the cases and bind up. So case 1 would be, there are infinitely many, so there are infinitely many n in n such that for every t greater than or equal to n, Bn is less than or equal to Bt. Okay, so let us take these n's, these infinitely many n's, right, in increasing order. Okay, let these n's, or I don't know how to write, yeah, let us be a little bit not rigorous. Let these n's be, okay, so the ones that satisfy this condition, the ones with the up arrows, I am going to call as n1, n2, n3 and so on. Okay, let these n's be, and I am going to take them, I am going to pick them in increasing order. Okay, I need to pick them in increasing order as I go ahead, right? The up arrows I am picking in increasing order, otherwise I will not get a subsequence of an. I need to pick them in increasing order, n1 less than n2 less than up to, and so on. So therefore what will happen is, what will happen here, we will have Bn1 and n2 is greater than n1, so this will be less than Bn2, okay, less than Bn3 less than or equal to, and so on. Okay, so this gives us a infinite increasing subsequence of Bn, but Bn anyway is a subsequence of An, so therefore this is a subsequence of An. Okay, and what happens in the other case? In the other case we exactly get infinitely many n in n such that for every t in t greater than or equal to n, Bn is greater than or equal to Bt. Okay, we will take these to be, let these n's be, okay, this is an infinite set, right? These n's are an infinite set. Actually this ni's are those, that set. Okay, let these be n1 less than n2 less than n3, we have to take an increasing order. So therefore what happens is Bn1, right, what does Bn1 satisfy, which property? It satisfies the property, or n1 satisfies the property that when t is greater than it, the next everything after it is less than it. So therefore this is going to be greater than or equal to Bn2, greater than or equal to Bn3, and so on. So we have got a decreasing subsequence, a simple technique. Okay, little notational, but the idea is easy. Okay, so now we will focus on trying to prove the Delvert's lemma. Yeah, we will try to prove Delvert's lemma, hopefully one version of it at least, the finite version of it. Let us see how we can. So for this we are going to talk about something called as, you all know what are chains? What is a chain in a poset? So chain is nothing but a subset of the poset okay, which is totally ordered. Every element is related to each other. Okay, so a nice place to talk about chains, because if you look at a total order, any subset would be a chain. Okay, not interesting. But say you look at n with division, can you give me some chains in n with division? So essentially you want to start with some a, find something greater than that, find something greater than that, find something greater than that, and so on. Yeah? Pairwise? Oh, what? That's not true. That's not true. I mean, I can take 6 and 8. That's right. 6 and 8. It doesn't work. Neither does 6 divide 8 nor 8 divide 6. Multiples of 8. Okay. But that would not be a chain. Everything would be related to A. But some 2, example, 2 times A and 3 times A are not related. These are both multiples of A. Any other one? Nice one? Think of starting with an element, finding something bigger than that. What would it mean by saying that this is bigger than this? It should be a multiple of this. And the next number should be a multiple of this. Number after that should be a multiple of that. Powers of A would work. Okay, one way of doing it would be powers of A. Anything else? We can go A times powers of n. Right, that's another option. A times powers of n. Okay. Essentially, you just need to start with an element, multiply something to it, take the next element, multiply something else to it, and go on. Okay, so those are the chains in n with division. So that's a chain, and we also define something called as an anti-chain. Okay, anti-chain would be no two elements are related. Okay, so the chain kind of gives us a sense of the length, and the anti-chain kind of gives you a sense of a width of the poset. Kind of some sense it goes along the width and length. We'll see that later. Okay, you can draw out posets. Okay, you can draw nice what do you call them, lattices for a poset. Okay, so the longest path would be the length which comes from the biggest chain, and the anti-chains would be those which are not related. Anyway, there is no path from A to B. That would be the you would want to pick such kind of elements. Anyway, let's have a look at what is this. So what is a chain? A chain a chain in a poset x with less than or equal to, okay, is a set S such that any two elements of S are comparable. Okay, any two elements of S are comparable. That is this thing. So of course you can't always put them in order like this, because we can do it because we are working in n with division, but you could have uncountably many elements in a chain also. Okay, like if you look at the chains of in R2 we had that other relation, right? A comma B is less than or equal to C comma D. If and only if A is less than or equal to C, B is less than or equal to D. Chains could have uncountably many elements in it. In fact, chains in R have uncountably many elements in it. So you should not be of the opinion that they have to be countable or something like that. Okay, so a chain in a poset. What is an anti-chain? An anti-chain in a poset, it's not a set which is not a this thing, that's not the definition. It's any two elements are not comparable. Yeah, examples here would be something like a square, or we can start with 1 also, a cube and so on, in n with division. Okay, in n with division, this is going to be a chain. Okay, this is a very nice poset in fact. Okay, anti-chain in a poset x comma less than or equal to is a set S such that, or we can go with such that no two distinct elements are comparable. Any example? Let's think about examples in n with division. Do we have any examples with n with division? Yeah, one nice one is there. Yeah, yeah, that's a nice one, right? We can look at the set of all primes, right? The set of all primes, that would be this thing. Even if you take the set of all primes and multiply it to something, that also gives you an anti-chain. Okay, so the set of all primes, set of all primes. You can even, you can't put 1 in it. So the set of all primes would be an anti-chain, right? 2, 3, 5, 7, whatever. None of them can be related. No prime can divide another this thing. Okay, so Dilbert's lemma talks about the sizes of chains and anti-chains. Okay, and as you will see that there seems to be some kind of a relation between the Dilbert's lemma and the the Erdos' theorem. Okay, so let's see. In fact, this is a little more general theorem because you can prove that from this with a smart manipulation. Okay, so the Dilbert's lemma is if x with less than or equal to is a poset. By the way, another nice poset is the power set of any set. If you look at the power set of any set with containment, have you all seen that? Have you all seen the lattice diagrams of those? The power set of x with containment, because we will be working that in the next section. The power set of, if x is a set, you look at the power set of x with containment. This is definitely a poset. I think all of you all can easily prove that. A is a subset of itself, 1. If A is a subset of B and B is a subset of A, then A equals B, right? Transitivity also is obvious. If A is a subset of B, B is a subset of C, then A is a subset of C. So that's easy. What would be the longest chains in that if x is finite? Okay, say with n elements in it. What do you think is the longest chain in this? What do you expect it to be? Not n. Starting with the empty set. Okay. So you can start with the empty set, put one element in it, right? Then throw another element inside it. Keep doing that. So it seems to be that that's the length of the longest chain. It is. What about an anti-chain? What would be the length of the longest anti-chain? Okay, so you can try drawing some lattice diagrams. Lattice diagrams are basically like this. So you could start with 1, 2, 3, 4, okay, and start with the empty set. This is a nice lattice diagram. It has a nice lower bound and a upper bound, supremum and infimum. Then above this you will have just the singleton sets. Okay, let's go with 3. Then above it you are going to have sets with 2 elements. So this actually gives you a nice, okay, you draw the arrows in the direction of the containment. Okay, so this will exactly give us the what is it? This will exactly give us the, it exactly tells you about the set. So when will 2 elements be related? If there is a path from one of them to the other, right? That's when will you get containment? If there is a path from one to the other, right? That's the natural this thing. So what will be the biggest anti-chain? Right? This one is actually, I think this is easy to see, I'm not sure. So no anti-chain obviously can contain this and this. So it looks like here at least this would definitely be an anti-chain. And there are others also, but this is an anti-chain. This, they are not related. These elements are not related. Neither these. So here it seems to be 3, but you can have a look at the others and try to increase number from 3 to 5, 3 to 4 to 5 and see whether you can find what is the biggest anti-chain. Anyway, we'll be doing that in the next section. So now we'll just prove the Dilbert's lemma. Okay, so if you have a poset of order, again, mn plus 1, m and n are natural numbers, fixed natural numbers, then either x with less than or equal to has a chain of length m plus 1 or an anti-chain. I don't want to say anti-chain of length, so I'm going to say anti-chain of size, because a chain looks like a length, right? But an anti-chain doesn't look like a length. So let's say of size, anti-chain of size n plus 1. Okay, so how do I prove this? First, again, this proof will resemble the proof of the Erdos-Szekeres theorem. What we do is we assume that this is so yeah, I assume that I cannot find any chain of length m plus 1. That means all chains are of length less than or equal to m. Okay, and I will take a mapping. Okay, so define. So suppose, so assume that I cannot find any chain of length m plus 1, and I will show that there is an anti-chain of length n plus 1. Okay, so suppose x with less than or equal to has no chain of length m plus 1. Okay, I'm going to define a very interesting function. So define, very easy actually, define f from, I'm going to go with mn plus 1. Let me write x as a1, a2 up to amn plus 1 for convenience. Right? I will give notation to the elements in x. Okay. So, or in fact I can, I need not do this, forget it. I can just take it from x to m, and what I will do is I'm going to define f of x to be the longest chain, okay, that starts with x, that longest chain that starts with, I think, with largest element x. That's possible. Okay, I can do that. So f of x is the longest chain okay, and we know that there is always going to be, because it's a finite set, so every chain will have a biggest element. Why? You just keep ordering it, right? You look through the entire thing and you keep, because of transitivity we can always find the biggest element. That can be proved. You can prove it by induction if you like. So longest chain, length of the longest chain, length of the longest chain with largest element x. Okay, and this is well defined because we have said that this has no chain of length m plus 1, right? So this is well defined. Okay, so therefore what happens is there's going to be a pullback by the pigeonhole principle. Therefore by the pigeonhole principle there exists some I here, there exists I in m such that f inverse of I, okay, the cardinality of f inverse of I is greater than or equal to the cardinality of x upon the cardinality of m. And what is this? This is mn plus 1 divided by m, okay, which we know is n plus 1 by m, which is strictly greater than n. Okay, so the cardinality of this is strictly greater than n. We have done this many times. Therefore, the cardinality of f inverse of I should be greater than or equal to n plus 1. Okay, and what we will show is that this is actually an anti-chain. F inverse of I is an anti-chain. Can anyone see why f inverse of I is an anti-chain? Can you see why f inverse of I is an anti-chain? What will happen if there are two elements which are related here? If you have two elements here which are related, say x and y are related, that means the longest element, the largest chain with largest element x will be I of length I, and also the largest chain of largest element y will be I. But these two are related. So if x is less than or equal to y, then you put y inside the x chain. Okay, so that's what you can do. So suppose x comma y is in f inverse of I and x is less than or equal to y, then what happens is f of x would be equal to f of y right, equal to I. So we can say let us call it as A1 less than A2 less than up to AI equals X be the longest chain with largest element, right. This is a chain with largest element X. This is a chain with largest element X. I'm going to say let this be the, I can get one, right, because f of x is the length of the longest chain with largest element X. So I can get one, but now Y is bigger than X, right, strictly greater than, right. I don't want them to be equal. So, but what you can see here is A1 less than A2 less than up to AI less than, which is equal to X, this is less than Y, and therefore we have a chain, right. Therefore is a chain of length I plus 1 with largest element Y. This is a contradiction, because the length of the largest chain with longest chain with largest element Y is I. That's a contradiction, right. So it contradicts what statement? It contradicts the statement that these two are related. So therefore, it contradicts this statement, okay. So therefore, for every x comma y in f inverse of I, what happens? X cannot be related to y, okay. Yeah. This is fine. Cannot be distinct elements afterwards. You will have this thing. Okay. So therefore, this is an anti-chain. Therefore, or in other words, you can say for every x comma y in f inverse of y, such that x is not equal to y, x is not less than or equal to y. Okay. So therefore, f inverse of I is an anti-chain of length n plus 1. So we assume that you have no chain of length m plus 1 and prove that you have an anti-chain of length n plus 1. So if there is no chain of length m plus 1, then there is an anti-chain of length n plus 1. That proves the Dilworth's lemma. Okay. There is also an infinite version of the Dilworth's lemma, which is not as easy to prove as the infinite version of the Erdos' theorem. Now, the small homework for you is to try to prove the Erdos theorem, finite version of the Erdos Erdos theorem using the Dilworth's theorem. Prove it as a corollary to this. Let's see who can do that. Okay. Yeah?